In this video, we are going to discuss acid-base titration. Here are the learning outcomes for these lessons. At the end of these lessons, students should be able to describe the titration process and distinguish the endpoint and the equivalence point. Students also need to sketch and interpret the variation of the pH against titer value for titrations. Students need to identify the suitable indicators for acid-base titration. Now, what is the meaning of the titration? Titration is a procedure for determining the concentration of a solution using another solutions of known concentrations that call standard solutions. In a titration, we have two types of solution. First, the titrant. Titrant is placed in the burette. The titrant is defined as a standard solution of a known concentration which is added to another solution whose concentration has to be determined. The next solution is the analyte. Analyte was placed in the conical flask. Analyte defined as the solution whose concentration has to be determined. In a titration, we'll obtain an equivalence point. The equivalence point is the point at which the amount of acid and base present exactly neutralizes one another. At equivalence point, the number of moles of hydroxide ion and the number of mole of hydronium ion are equal and the neutralization is complete. The equivalence point can be identified by using a graph that is called titration curve. The endpoint. The endpoint of a titration is the point at which the indicator changes color. The addition of an indicator to the analyte solutions helps us visually spot the equivalence point in an acid-base titration. This picture shows how to visualize a good endpoint during a titration. The indicator. Indicator is a substance that is added to the solution at which undergoes some sort of color change when reaction is over. In acid-base titrations, indicators are substances that have distinctly different colors in acidic and basic medium. The endpoint of a titration occurs when the indicator changes the color. By choosing the proper indicator for a titration, we can use the endpoints to determine the equivalence point. We have to choose an indicator which the endpoint pH range lies on the steep part of the titration curve. This choice ensures that the pH at the equivalence point will fall within the range over which indicator changes color. Here are some common indicators that can be used during a titration. To choose the suitable indicators, we can use the endpoint pH range as a reference. For a strong acid and a strong base reaction, the pH range is between 3 to 11. For a reaction between weak acid and a strong base, the pH range is between 7 to 11. And the reaction between the strong acid and the weak base, the pH range is between 3 to 7. The pH range is defined as the range over which the indicator changes from the acid color to the base color. Now, let's discuss the titration curve. Titration curve is the plot of the pH of the analyte solutions versus the volume of the titrant added as the titration progresses. Let's discuss for the strong acid, strong base titrations. Let's have an example of a titration for hydrochloric acid and the sodium hydroxide. Hydrochloric acid reacts with sodium hydroxide to produce sodium chloride salt and water. If we start plotting the pH of the analyte of the hydrochloric acid against the volume of the sodium hydroxide that we are adding from the burette, we will get a titration curve as shown. There are four important points in a titration curve. Point 1, it is a point before addition of a strong base. Point 2, it is the point before the equivalence point. Point 3 is the point at equivalence point. And point 4, the point after the equivalence point. First, let's discuss at point 1. At this point, no sodium hydroxide is added yet. Therefore, only hydrochloric acid is in the conical flask, which means it is predominantly contains the H+ ion from the dissociation of the hydrochloric acid. Thus, the pH of this analyte is low, about 1.0. At point 2, when sodium hydroxide is added slowly into the hydrochloric acid in the conical flask, the pH increases slowly until just before the equivalence point. When one more drop of sodium hydroxide is added, the pH changes sharply from 3 to 11, which is we can observe at the steep part of the titration curve. The reaction occurs between the hydrochloric acid and the sodium hydroxide to produce the salt of sodium chloride and water. At the equivalence point, the moles of sodium hydroxide added is equal to the mole of hydrochloric acid in the analyte. The H+ ions are completely neutralized by the hydroxide ions. Therefore, the solution only has a salt of sodium chloride and water. The sodium chloride salt is do not hydrolyze. Thus, at equivalence point, the pH is equal to 7, which is, it is a neutral salt. After the equivalence point, the addition of sodium hydroxide continues. pH starts becoming basic because the hydrochloric acid has been completely neutralized, and now excess of hydroxide ions are present in the solution, which is from the dissociation of the sodium hydroxide. The excess hydroxide ion making the solution basic. Thus, the pH must be greater than 7. To choose the suitable indicators for the reaction, we can observe the pH at equivalence point. For the reaction between the strong acid and strong base titrations, the equivalence point has a pH equals to 7. Thus, the sodium chloride salt is a neutral salt because the sodium chloride do not hydrolyze. Therefore, to choose the suitable indicators, the pH range must be between 3 to 11. Here are some examples of the indicators with pH range within 3 to 11, which is we can use bromophenol blue, bromothymol blue, or phenolphthalein. To sketch a titration curve, we have to consider the type of analyte and the titrant used during a titration. The pH that is plotted in the graph, it is referred to the pH of the analyte used in the conical flask. The shape of the titration curve depends whether the solution in the conical flask is a basic or an acidic solution. Now, let's discuss the strong acid and weak base titrations. Let's have an example of reaction between the hydrochloric acid and ammonia solutions. Hydrochloric acid is a strong acid which is react with ammonia of a weak base to form salt of ammonium chloride. If we start plotting the pH of the analyte of the hydrochloric acid against the volume of ammonia that we are adding from the burette, we will get a titration curve as shown. There are four important points in a titration curve. At point 1, it is the point before the addition of the weak base. Point 2, it is the point before the equivalence point. Point 3, the point at equivalence point. And point 4, after the equivalence point. Let's start with point 1. At this point, no ammonia is added yet. Therefore, only hydrochloric acid is in the conical flask, which means it is predominantly contains the H plus ion from the dissociation of the hydrochloric acid. Thus, the pH of this analyte is low, about 1.0. At point 2, when ammonia is added slowly into the hydrochloric acid in the conical flask, the pH increases slowly until just before the equivalence point. When one more drop of ammonia is added, the pH changes sharply from 3 to 7, which we can observe at the steep part of the titration curve. The reaction that occurs in this titration, which is the hydrochloric acid react with ammonia to give the salt of ammonium chloride. At equivalence point, the moles of ammonia added is equals to the moles of the hydrochloric acid in the analyte. The hydrogen ions are completely neutralized by the hydroxide ions. Thus, the solution only has an aqueous salt of ammonium chloride. But the pH is not neutral. Why? At the equivalence point, the solution only has ammonium ion and the chloride ions. The ammonium ions is the strong conjugate acid of a weak base ammonia. Thus, ammonium ions is hydrolyzed with water. The presence of the H3O+ ions making the solution acidic. Thus, at equivalence point, the pH must be less than 7. After the equivalence point, the addition of ammonia continues. The pH starts becoming basic because the hydrochloric acid has been completely neutralized, and now excess hydroxide ions are present in the solution, which is from the dissociation of the ammonia. The excess hydroxide ion making the solution basic, thus the pH is greater than 7. To choose the suitable indicators, we can observe the pH at the equivalence point. For the reaction between strong acid and the weak base titrations, the equivalence point has a pH less than 7. Thus, the ammonium chloride for this reaction is an acidic salt. This is because ammonium chloride salt is hydrolyzed with water. The suitable indicators that can be used in this reaction have a pH range between 3 to 7. The example of the suitable indicators, such as bromophenol blue, methyl orange, or methyl red. To sketch a titration curve, we have to consider the type of analyte and the titrant used in the reaction. The pH that has been plotted in the graph is referred to the pH of the analyte used during the titrations. The shape of the titration curve depends on the pH change of the analyte used in the reaction. Now, let's discuss the weak acid and the strong base titrations. Let's have an example of reaction between the ethanoic acid and the sodium hydroxide. Ethanoic acid react with sodium hydroxide to give sodium ethanoate salt and water. If we start plotting the pH of the analyte of the ethanoic acid against the volume of sodium hydroxide that we are adding from the burette, we will get a titration curve as shown. There are 4 important points in the titration. Point 1, the point before the addition of a strong base. Point 2, the point before the equivalence point. Point 3 is the point at equivalence point, and point 4, the point after the equivalence point. Let's start with point 1. At this point, no sodium hydroxide is added yet. Therefore, only ethanoic acid in the conical flask, which means it is predominantly contains the H3O+ ion from the dissociation of the weak acid. The pH of this analyte is low, which is about 3, because the ethanoic acid is a weaker acid. Point 2. When sodium hydroxide is added slowly into the ethanoic acid in the conical flask, the pH increases slowly until just before the equivalence point. When one more drop of sodium hydroxide is added, the pH changes sharply from 7 to 11, which is we can observe at the steep part of the titration curve. The reaction occurs between the ethanoic acid and the sodium hydroxide, forming the sodium ethanoate salt and water. At equivalence point, the moles of sodium hydroxide added is equals to the moles of ethanoic acid in the analyte. The H+ ion are completely neutralized the hydroxide ions. Thus, the solution has only an aqueous salt of sodium ethanoate. But the pH is not neutral. Why? At equivalence point, the solution has ethanoate ion and the sodium ion. Since the ethanoate ion is a strong conjugate base of a weak acid, thus ethanoate ions is hydrolyzed with water. The presence of the hydroxide ion making the solution become basic. Thus, at equivalence points, the pH must be greater than 7. After the equivalence point, the addition of sodium hydroxide continues. The pH starts becoming basic because the ethanoic acid has been completely neutralized, and now excess hydroxide ions are present in the solution, which is it formed from the dissociation of the sodium hydroxide. The excess of hydroxide ion making the solution basic. Thus, the pH must be greater than 7. To choose a suitable indicators, we can observe the pH at equivalence point. For a reaction between weak acid and a strong base titration, the equivalence point has a pH greater than 7. In this reaction, sodium ethanoate salt is a basic salt because the sodium ethanoate is hydrolyzed with water. The suitable indicators can be chosen in the pH range between 7 to 11. For example, the bromothymol blue, the cresol red, and the phenolphthalein. To sketch a titration curve, we can consider the type of analyte and the titrant used. The pH that has been plotted in the graph is referred to the pH of the analyte used during the titrations. The shape of the titration curve depends on the pH change of the analyte used during the titrations. Now, let's discuss on how to calculate the pH in acid-base titrations. This is an example question on how to performing the calculations of pH of a titrations. In these questions, we have to calculate the value of pH and sketch the titration curve for the titrations. This is the second question. In these questions, we have to choose the most suitable indicator for the titration from a given list of indicators in the table. Now, let's answer the first questions. Calculate the pH before the addition of the sodium hydroxide. Before the addition of the sodium hydroxide, only hydrochloric acid is present. Thus, the pH is determined by the H+ ion present from the dissociation of the hydrochloric acid. HCl is a strong acid. The strong acid is completely dissociated in the solution. Thus, the concentration of the hydrochloric acid must be equal to the concentration of the hydrogen ion, which is equals to 0.1 molar. Thus, the pH can be calculated using negative log of H+ concentration, which is give and equals to 1. Now, let's answer the second question. The question is, calculate the pH at half equivalence point. At equivalence point, most of sodium hydroxide added is equals to the moles of hydrochloric acid in the analyte. By using the formula of MAVA equals to MBVB, we can determine the volume of the sodium hydroxide used at equivalence point, which is equals to 25 ml. Therefore, the volume of sodium hydroxide at half equivalence point is 12.5 ml. Then, we can calculate the number of mole of sodium hydroxide used in the reaction, which is equals to 1.25 exponent negative 3 mole, and the moles of hydrochloric acid used is 2.50 exponent negative 3 moles. The total volume of a solution is equals to 37.5 milliliter. By using the ICF table, we can determine the final composition of the reaction. From the ICF table, we can observe the final concentration for the hydrochloric acid is remain with 0.0333 molar, and the sodium chloride form with 0.0333 molar. That shows the sodium hydroxide is completely consumed during the reaction. After the reaction, the sodium chloride salt formed with the presence of excess hydrochloric acid. The sodium chloride is a salt of strong acid and base. Thus, the salt is do not hydrolyze. Therefore, the presence of H+ from the remaining hydrochloric acid will determine the pH of the solutions. By calculating the pH using the formula of pH equals to negative log H+ concentrations, we'll obtain the pH value with 1.48. Now, let's calculate the pH at equivalence point. At equivalence point, the moles of sodium hydroxide is equals to the moles of hydrochloric acid. Since mole of hydrochloric acid available in the flask is 2.50 exponent negative 3 mole, thus the mole of sodium hydroxide needed must be equals to 2.50 exponent negative 3 moles. By using the ICF table, we can determine the final composition of the reaction. At the end of the reaction, we can see that is hydrochloric acid and the sodium hydroxide is completely consumed in the reaction. Thus, it formed 2.50 exponent negative 3 moles of the salt. The sodium chloride salt is do not hydrolyze. Thus, the pH is equals to 7, which means the salt is a neutral salt. Now, let's calculate the pH after the addition of 30 ml of sodium hydroxide. First, calculate the number of mole for acid and base used in the reaction. The moles of sodium hydroxide used in the reaction is 3.00 exponent negative 3 moles, and the hydrochloric acid with 2.50 exponent negative 3 moles. The total volume of the solution is equals to 55 milliliter. By using the ICF table, we can determine the final composition of the reaction. From the ICF table, we can observe that hydrochloric acid is completely consumed. But sodium hydroxide still have a remaining 0.0091 molar. And the sodium chloride salt form 0.0455 molar. After the reaction, we can observe that sodium chloride salt is formed with the presence of excess sodium hydroxide. The sodium chloride is a salt of a strong acid and base, thus the salt is do not hydrolyze. Therefore, the presence of hydroxide ion from the remaining sodium hydroxide will determine the pH of the solution. But before that, we have to calculate the value of POH from the base. By using the formula of POH equals to negative log of OH minus concentrations, substituting the value will obtain the POH value with 2.04. To determine the pH, We can use the formula of pH equals to 14 minus pOH. That will obtain the pH equals to 11.96. By using the pH value obtained from the calculations, we can plot the titration curve for the reaction between the hydrochloric acid and the sodium hydroxide. Now, let's answer question B. Which is the most suitable indicator for this reaction? The most suitable indicator for this reaction is bromothymol blue. This is because the range covers the endpoint of this titration, with a pH range between 3 to 11. The starting range just before the endpoint and shows the drastic or abrupt color change. Now, you can try to answer these exercise questions to improve your understanding. That is the end of our lessons today. Bye-bye.